Hello. Today we will study about signal space representation and its application in a digital communication system. So this is the outline of the lecture. So we will first study about the geometric representation of signals. What is a signal exactly in a signal space? Then we will study about Gram-Schmidt orthogonalization procedure. So once we are done with that, we will move on to how it is the concepts are applied in a digital communication system. So we'll study about the conversion of an AWN channel, an AWGN channel, conversion of AWGN channel into a vector channel. Then we will study about maximum likelihood decoding or ML decoding, then correlation receiver, and how the probability of error of a communication system is related with all these things. So this is the outline. So we'll start with the concept of signal space. So what exactly is a signal space? So actually the concept of signal space says that a set of signals, so that should satisfy some conditions that we will see later. A set of signals can be represented as a set of vectors. So a vector. So a vector can be represented as a set containing some numbers as a tuple. Then if a signal can be represented as a set of vectors, the advantage is that the concepts of vector fields can be used to analyze the properties of the various signals when it is used in a communication system. So the signal can be viewed as an n-dimensional vector or an n-tuple. So this n-dimensional vector is actually, it is a point in the n-dimensional vector space. So a signal can be represented as a point in an n-dimensional vector space. That is the idea. Then this vector bears an one-to-one relationship with the signal. So that is, each signal will have a different vector representation within that signal space. So we'll see the details. So this says that consider you have a signal x of t. So this x of t can be ultimately represented as an n-dimensional vector x1, x2, etc. xn. So this is done with the help of what is called as some basis signals which are n in numbers. So it is represented as an n signal set phi n of t. It has n basis signals. We'll see what are the properties of this basis vectors, but for now we can call it as a set phi n of t which has n members, phi 1 of t, phi 2 of t, etc. to phi n of t. And the most important thing is that all these n signals which forms this basis set should be linearly independent. Now we have seen we have seen the coefficients and we have seen the basis vectors or basis functions. Then I can write x of t as equal to x1 phi 1 of t plus x2 phi 2 of t, etc. xn phi n of t, that is equal to sigma k equal to 1 to n xk phi k of t. So this is similar to our normal coordinate system where a vector is represented as a combination of some basis vectors, like we have seen it 3i plus 4j plus 5k, that is the point 3 4 5 in the 3D space. The vector 3i plus 4j plus 5k is the point 3 4 5 in the 3-dimensional space. So here we are considering an n-dimensional space. and a signal x of t can be represented as x1 phi1 of t plus x2 phi2 of t plus etc xn phi n of t, and this phi1 of t, phi2 of t, phi n of t are called as the basis vectors, and it will span the n-dimensional signal space. So if every single signal x of t in a certain signal space can be represented as a linear combination of phi n of t, then we have an n-dimensional signal space. If all the signals in the signal space can be represented as a linear combination of this basis signals, then we can say that we have an n-dimensional signal space. Now this set of I n of t is called as the basis signals. They should be orthonormal. These basis signals are orthonormal. So you know what is orthogonal? Orthogonal means that two signals are orthogonal when their inner product is 0. Then orthonormal means that the energy of the signal is, or energy of the individual basis functions is unity. That condition also should be satisfied. That is, if the inner product of phi j of t and phi k of t, that is integral minus infinity to infinity phi j of t into phi k of t, equal to 0 if the signals are different, that is if j not equal to k. Otherwise it becomes integral minus infinity to plus infinity phi j square of t, or it is the energy of the signal that should be equal to 1. So this, if this condition is satisfied, then we say that this set represents a set of orthonormal basis function. Now we will see how the coefficients x1, x2, etc. up to xn are found out. So consider integral minus infinity to infinity x of t into phi j of t. That is the projection of x of t along the direction specified by phi j of t. That is actually inner product of x of t and phi j of t. So consider that. So we can write x of t as sigma k equal to 1 to n x k phi k of t phi j of t dt. So it is very clear that the RHS is valid only when j equal to k, because otherwise phi k of t into phi j of t is 0. So we assume that j and this, it has value only when j is equal to k and its value is 1. So RHS becomes xj. So we can write xj equal to integral minus infinity to infinity x of t into phi j of t dt. That is the coefficient, the jth coefficient is equal to the projection of x of t along the direction specified by phi j of t. Okay. These concepts are almost similar to the ones that we study in our linear algebra or this vector space. Now we will consider the orthogonal expansion of signals using the principles that we studied before. So you consider a signal s of t that is deterministic and real valued, and s of t should be finite energy signal. That means that the energy of the signal Es is integral minus infinity to infinity s square of t dt less than infinity. ഇതിൽ മനസ്സിലാക്കാനുള്ള കാര്യം എന്ന് വെച്ചാൽ, ഫൈനൈറ്റ് ആയിട്ട് എനർജി ഉള്ള സിഗ്നൽസിനെ മാത്രമേ നമുക്ക് ഈ കമ്മ്യൂണിക്കേഷൻ സിസ്റ്റത്തിലെല്ലാം ഉപയോഗിക്കാൻ പറ്റുള്ളൂ. അതിനെ മാത്രമേ നമുക്ക് ഒരു സിഗ്നൽ സ്പേസിൽ റെപ്രസെൻ്റ് ചെയ്യാനും പറ്റുള്ളൂ. So you know, if the energy is infinite or the signal is not an energy signal, then it is unstable. That we usually study in signals and system. Okay, so we consider a real valued finite energy signal and let phi n of t, where n is equal to 1, 2, etc. up to capital K exist. So this phi n of t is actually a basis set, so which contains k basis functions, capital K basis function. Now we don't know whether this s of t can be represented using this capital K basis functions correctly? We don't know. So we assume that we approximate S of t by a weighted linear sum. S cap of t is equal to sigma k equal to 1 to capital K sk into phi k of t. So this is an approximation for S of t using our basis functions. So since this is an approximation, we can define an error signal E of t as S of t minus S cap of t. So that is the error signal, S of t minus S cap of t. Our problem will be to select the coefficients sk in such a way that the error is minimized. Okay. The error should be minimum. So in the case of the signals, we can say that the energy of the error is minimum. That is, we need to find the coefficients in such a way that the energy of the error signal E equal to integral minus infinity to infinity E square of t dt is minimized. So we can substitute for E of t as S of t minus S cap of t. Then we can substitute for S cap of t. Then to minimize the error, or to minimize the error in such a way that, or to find the coefficient such a way that error is minimized, we need to differentiate the error with respect to the coefficient and equate it to 0. So take dou EE by dou Sj equal to 0 for j equal to 1, 2, etc. up to k. So we have k coefficients. So when we are taking the derivative, it is 2 into integral minus infinity to infinity S of t minus sigma k sk phi k of t into minus phi j of t dt equal to 0. So the second term is valid only when j equal to k, and when j equal to k, the second term becomes sj. And if we take sj to the other side, we will get the coefficient sj as integral minus infinity to infinity S of t into phi j of t dt. So this is similar to the one that we studied earlier. That is, the coefficients are obtained by projecting signal S of t to each phi j of t. That is, the coefficients can be obtained by projecting the signal S of t to each of phi j of t. Phi j of t ലേക്കുള്ള പ്രൊജക്ഷൻ, അതാണ് ഇന്നർ പ്രോഡക്റ്റ് ബിറ്റ്വീൻ എസ് ഓഫ് ടി ആൻഡ് phi j of t. അതെടുത്താൽ നമുക്ക് ആ ഓരോ സ്ഥലത്തേക്കുള്ള കോഎഫിഷ്യൻസ്, ഇൻഡിവിജ്വൽ കോഎഫിഷ്യൻസ് കിട്ടും. So thus S cap of t is, so we can write S cap of t as projection of S of t into the k dimensional signal space spanned by phi n of t, where n varies from 1 to k. അപ്പോൾ ഈ സിഗ്നൽ എസ് ക്യാപ്പ് ഓഫ് ടി എന്ന് പറയുന്ന അപ്രോക്സിമേഷൻ എന്താണെന്ന് വെച്ചാൽ, നമ്മൾ എസ് ഓഫ് ടിയെ ഈ കെ ഡയമെൻഷണൽ സിഗ്നൽ സ്പേസിൻ്റെ ഓരോ സ്പേസിലേക്കും പ്രൊജക്റ്റ് ചെയ്യുന്നു, അതിൻ്റെ എല്ലാം കൂടെ സം എടുക്കുന്നു. ആണല്ലോ നമ്മളവിടെ ചെയ്തിരിക്കുന്നത്. സിഗ്മ കെ എസ് കെ ഫൈ കെ ഓഫ് ടി. ഓരോ എസ് കെ എന്ന് പറഞ്ഞാൽ എസ് ഓഫ് ടി ഫൈ ജെ ഓഫ് ടി ആണ്. അപ്പോൾ എസ് ഓഫ് ടിയെ നമ്മൾ ഓരോ ബേസിസ് ഫങ്ഷനിലേക്കും പ്രൊജക്റ്റ് ചെയ്യുന്നു, അതിൻ്റെ എല്ലാം കൂടെ സം എടുക്കുന്നു. അപ്പോൾ എറർ മിനിമൈസ് ചെയ്യണമെങ്കിൽ ദ കോഎഫിഷ്യൻ്റ് എസ് ജെ ഷുഡ് ബി ഇൻറ്റഗ്രൽ മൈനസ് ഇൻഫിനിറ്റി ടു ഇൻഫിനിറ്റി എസ് ഓഫ് ടി ഫൈ ജെ ഓഫ് ടി. അങ്ങനെ ആയിരിക്കണം. Now consider the inner product between the error signal and S cap of t. The approximation signal, error signal നമ്മൾ inner product എടുക്കുകയാണ്. So that is E of t sigma k sk phi k of t dt. So integral minus infinity to infinity E of t sigma k S of t phi j of t phi k of t dt സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്തു. ഇപ്പോൾ നമുക്കറിയാം phi j of t into phi k of t, its value is 0. It has value only when j equal to k. So here otherwise it is 0. So we can say that the inner product between the error and the signal approximated is 0. That is, error is orthogonal to the k dimensional space. So that is an important concept. Error is orthogonal to the k-dimensional space means that it again means that error is orthogonal to each of the individual k basis functions, phi 1 of t, phi 2 of t, etc., phi k of t. It's a very important inference. The error signal is orthogonal to each of the basis functions, phi 1 of t to up to phi k of t. Error is orthogonal. Means that the projection of error onto those spaces is 0. So for minimum energy, E min is equal to integral minus infinity to infinity E square of t. So E of t into S of t minus S cap of t. So we have seen that integral minus infinity to infinity E of t into S cap of t is 0. So we use that. So it is E of t into S of t. Substitute S of t minus S cap of t as E of t. So we'll get this as integral minus infinity to infinity S square of t dt minus integral minus infinity to infinity sigma k S k phi k of t into S of t. We have substituted for S cap of t. Now this integral sk into phi k of t is sk, or the integral s of t into phi k of t, integral minus infinity to infinity s of t phi k of t is actually the coefficient sk. So I can write this as ultimately as the first time integral minus infinity to infinity s square of t dt is actually the energy of s of t. So it is equal to Es minus sigma k equal to 1 to k. Sk into sk is sk square. So that is the energy equal to Es minus sigma k equal to 1 to k sk square. So for minimum energy, that is when E min is equal to 0, then you will get Es is equal to sigma k equal to 1 to k sk square. So that is the idea. For minimum energy, the energy of the signal should be equal to sum of all the coefficients. That all should be equal. Okay. Now if every finite energy signal can be represented as S of t equal to sigma k equal to 1 to k sk phi k of t, that is if every finite energy signal within that signal space can be represented as S of t equal to sigma k equal to 1 to k sk phi k of t and E min equal to 0, then the set phi n of t, that is n equal to 1 to k, this the all the k basis functions or this set is said to be complete. Now we have studied that a signal can be represented as a point in an n-dimensional space or a k-dimensional space, and this is done with the help of orthonormal basis functions. Now we will study how this orthonormal basis functions can be constructed. It's a most important method or most popular method for constructing a set of orthonormal basis function is called as the Gram-Schmidt orthogonalization procedure. So that we will study it now. So consider a set of finite energy signals, m finite energy signals, capital M. Capital M is the total number of signals that we are considering. So represent it as Sm of t, where m varies from 1 to capital M. So for this set, we wish to obtain a set of orthonormal basis functions. That means that we need to get some phi of t, a set phi of t, which contains some n, capital N number of signals, in such a way that using the linear combination of those signals, we can represent all the signals Sm of t, all the signals Sm of t, all the capital M signals. We should be able to represent all the capital M signals as a linear combination of our basis function. So this Gram-Schmidt process exactly gives that. So it gives a set of basis functions which can be used to represent our energy our signal Sm of t as a linear combination, or this Sm of t's will be converted to, each S of t will be converted to a vector in that space spanned by phi of t. So we'll study what is the procedure. The first procedure, the first step, we will take phi1 of t as S1 of t by root t1. So we know that phi1 of t should be having the norm as 1. We have already seen this is orthonormal. So each is having the norm as 1. So to make norm as 1, we will first take S1 of phi1 of t as S1 of t by root of its energy. Then you can see that the norm becomes 1. If you divide a signal by its root of its energy, its modulus or its norm or its energy, it becomes 1. Okay. Now what will in the next step take S2 of t. So next second signal, and define a coefficient S21, that is a projection of S2 of t onto phi1 of t. That is S21 is equal to integral minus infinity to infinity S2 of t into phi1 of t dt. Okay. So find the coefficient S21, that is a projection of S2 of t onto the basis function phi1 of t. So that is as S21 is equal to integral minus infinity to infinity S2 of t into phi1 of t dt. Now define a new intermediate signal, that is G2 of t equal to S2 of t minus S21 into phi1 of t. Now we can compare this with our old expression. G2 of t is actually an error signal. So it is a error between S2 of t and its approximation using phi1 of t. It's very clear. So we define a new intermediate signal called G2 of t, which is the difference between S2 of t and S21 into phi1 of t. So this is actually, we can see that this is actually the error between the second signal S2 of t and its approximation using phi1 of t. So we have already derived that the error signal is actually orthogonal to each of the basis functions. So we have proved it, or we have derived it before. So we know that this error signal will be orthogonal to phi1 of t, because error is orthogonal to all the basis functions that we have derived before. So we know that this error will be orthogonal to phi1 of t. So that gives, or we can use that to define the second basis function, because we have now got a signal that is orthogonal to our first basis function. We know that all the basis functions should be orthogonal to each other. Now we have got G2 of t that is orthogonal to phi1 of t. So we can define phi2 of t as G2 of t by root of energy of G2 of t. So we have to make its norm or its energy equal to 1. That is a requirement. So that is why we define phi2 of t as G2 of t by root of energy of G2 of t. So that is equal to G2 of t by root of integral minus infinity to infinity G2 square of t dt. So that is S2 of t, G2 of t is S2 of t minus S21 into phi1 of t by root of. So if you substitute for G2 square of t dt, you will get it as root of E2 minus S21 square. This also we have derived before. The energy energy of the error, that is actually energy of the signal minus sum of coefficients, that we have derived before. So G2 of t by root of the energy of G2 of t is actually, we can write that as S2 of t minus S21 into phi1 of t by root of E2 minus S21 square. Now we got the second basis function also. In the next step, to find the third basis function, here we have to find two coefficients. S31 is a projection of S of t on phi1 of t, and S32, that is a projection of S31 is projection of S3 of t on phi 1 of t. So there is that 3 is missing. Then S32 is the projection of S3 of t on phi 2 of t. So define the intermediate signal G3 of t is equal to S3 of t minus S31 into phi 1 of t minus S32 into phi 2 of t. So this is an error signal. That is, this is the error between the signal S3 of t and its approximation on phi 1 of t and phi 2 of t, or approximation on the 2D space defined by phi 1 of t and phi 2 of t. This is the error signal. So this error will be orthogonal to both phi 1 of t and phi 2 of t. Then we have studied before. So we have got a signal G3 of t which is orthogonal to both phi 1 of t and phi 2 of t. So we can consider that as our next basis function, but we need to normalize it, or we need to make its energy 1. So phi 3 of t is equal to G3 of t by root of energy of G3 of t. So we get phi 3 of t is equal to S3 of t minus S31 into phi 1 of t minus S32 into phi 2 of t by root of energy of G3 of t we have already derived before, energy of the error. It is energy of the signal minus sum of coefficients. So E3 minus S31 square minus S32 square. So generalizing it, we can write in general the intermediate signal Gi of t is Si of t minus sigma j equal to 1 to I minus 1 Sij into phi j of t. That is our current signal minus the projection of the signals on all the basis functions up to I. So this is something like an error, or this is the error between the signal and its approximation. So that error will be normal to or orthogonal to each of the basis function. And here the coefficient Sij is integral minus infinity to infinity Si of t into phi j of t. Okay. And so this Gi of t is orthogonal to each of the basis functions. So the new basis function can be represented as the normalized value of Gi of t, that is Gi of t with its energy made to 1. So Gi of t by root of its energy. So Gi of t can be represented Si of t minus sigma j equal to 1 to I minus 1 Sij into phi j of t, that is by root of Ei minus sigma j equal to 1 to I minus 1 Sij square. Energy of the error signal is energy of the signal minus sum of the squares of the coefficients. So this is continued until, this process continued until all the m signals have been exhausted and we get n less than or equal to m orthonormal basis functions. So we get a maximum of m basis functions. Sometimes some of the signals, or sometimes all the m signals may not be linearly independent. Some signal may be linear combination of some other signal. In that case we will get only capital N less than m orthonormal basis function. Maximum we will get m basis functions. Sometimes if the set contains some signal which is a function of some other signal, then we will get only lesser number of basis function. So ultimately we will get capital N, it may be equal to m if all the signals are linearly independent, or if there are some dependent signals there, we will get less number of orthonormal basis functions. We will define the number of basis functions as capital N, which will be always less than or equal to m. Then the number of basis functions is actually the dimension of the signal space. The dimension of the signal space is represented as capital N, which is less than or equal to m. And when n equal to m, when will be n equal to m? When all the capital M signals are linearly independent. Now we will see an example where we use Gram-Schmidt process to obtain a basis function set for the following signal set. So you have 4 signals, S1 of t, S2 of t, S3 of t and S4 of t. So we need to find we need to find an orthonormal basis function set to represent these 4 signals. Okay, so we'll proceed. The first step is phi 1 of t equal to S1 of t by root t1. So you can see that S1 of t is having an energy root 2. You can do it. Sorry, its energy is 2. S1 of t is having an energy 2. So phi 1 of t will be S1 of t by root t1, that is S1 of t by root 2. Now we will find S21. S21 is actually integral 0 to 2 S2 of t into phi 1 of t. So phi 1 of t is S1 of t by root 2. So when you do that, S2 of t into phi 1 of t is equal to integral 0 to 1 dt plus, it is actually 1 by root 2 dt. Phi 1 of t has by root, I missed it. So it is actually 1 by root 2 dt. So integral 0 to 1 by root 2 dt plus 1 to 2 minus 1 by root 2 dt is 0. So straight away we get that S2 of t and phi 1 of t are orthogonal because S21 is 0. So we don't have to find that intermediate signal. Or intermediate signal is G2 of t is S2 of t itself, because the other coefficient is 0, S21. That is the projection of S2 of t on phi 1 of t is 0. So phi 2 of t is equal to S2 of t by root t2. Now E2 is also having energy as 2. So phi 2 of t is S2 of t by root 2. So you can see S2 of t will be also having an energy 2. Now find the coefficient S31. S31 is integral S3 of t into phi 1 of t dt. So when you do that integral, you will get it as root 2, and you will get S32 as integral S3 of t into phi 2 of t, it is equal to 0. So you do all the steps. So I have missed some steps. So you can do all the steps when you study. Now G3 of t is, that is intermediate signal, is equal to S3 of t minus root 2 into phi 1 of t. So it is equal to minus 1 when 2 less than or equal to t less than or equal to 3, 0 otherwise. So energy of G3 of t is 1. So G3 of t, you can do the steps. Okay. So G3 of t is having an energy 1. You can see G3 of t is having a value minus 1 between 2 and 3. So integral 2 to 3 minus 1 the whole square dt will be 1. That is the energy of G3 of t is 1. So you can directly take phi 3 of t equal to G3 of t. Now to obtain phi 4 of t, we find S41 equal to minus root 2, S42 equal to 0, S43 equal to 1. That is the projection of S4 of t on all the previous 3 basis functions. S41 will get it as minus root 2, S42 will get it as 0, and S43 will get it as 1. So hence G4 of t is equal to S4 of t minus S41 into phi 1 of t. So that is plus root 2 phi 1 of t. S42 is 0 minus S43 is 1 into phi 3 of t. So when you do that, you will get G4 of t is 0. So that means that phi 4 of t is 0. So this means that one basis function, you will get the value as 0. That means that one signal can be represented as the linear combination of the other signal, or that the 4 signals S1 of t to S4 of t is not linearly independent. One signal can be represented as linear combination of the other signal. So that is why we got 3 signals, and these 3 signals are enough, or 3 basis functions are enough to represent all the 4 signals S1 of t to S4 of t. So all the 4 S1 of t to S4 of t can be represented as the linear combination of phi 1 of t to phi 3 of t. So to find the coefficient, that you can do it as a assignment. So I'll give you that as an assignment. To find the coefficients of each of the signals, or to convert each of those signals to the vector. So here you can see that this signal space is having a dimension of 3. You are having only 3 basis functions. Although your set has 4 signals, each signal can be represented using 3 basis functions, phi 1 of t, phi 2 of 3 and phi 3 of t, or each signal is a 3 tuple. Each signal can be represented as a set of 3 numbers. So you need only 3 basis functions here, because one base function is 0. So what are some of the inferences? Say general signal Sm of t can be represented as sigma n equal to 1 to capital N Smn phi n of t. That is, each signal is an n tuple. It contains n values, or it is a vector. It is a vector, or we can vector containing n components, or again it is a point in n dimensional space. Each set of m signals is an n tuple, or it is a point in the n dimensional space. So actually you have to use capital N here. The small n is a variable, capital N is the total number of variables. So each signal is a capital N tuple, or a vector which contains capital N components, and each point is in a capital N. Each signal is a point in capital N dimensional subspace. So we can write the vector as, or Sm of t as a vector. So you can see here Sm of t is a vector. Sm is equal to Sm1, Sm2 up to Smn. That is a point in capital N dimensional subspace. Please correct that. It is not small n dimensional. It is a point in capital N dimensional space. Now this vector Sm is called as a signal space representation or constellation. So we will use this constellation very often in the future lectures. So constellation means it is the signal space representation of the signal Sm of t. ഒരു സിഗ്നലിൻ്റെ കോൺസ്റ്റലേഷൻ എന്ന് പറയുന്നത് phi 1 of t, phi 2 of t, phi 3 of t ഇതെല്ലാം കൂടെ ചേർന്നിട്ടൊരു സ്പേസ്, ഒരു n ഡയമെൻഷണൽ സ്പേസ് ഉണ്ടാവും. ആ സ്പേസിൽ ഒരു പോയിൻ്റ് ആയിരിക്കും ഈ സിഗ്നൽ. അപ്പോൾ ഈ സിഗ്നൽ, അല്ലെങ്കിൽ ഈ ക്യാപിറ്റൽ എം സിഗ്നൽസ് ഉണ്ടെങ്കിൽ അതെല്ലാം എവിടെയാണോ കിടക്കുന്നത് അതിനെല്ലാം കൂടെ ചേർത്ത് നമ്മൾ ആ ഒരു സ്പേസിൽ n ഡയമെൻഷൻ സ്പേസിൽ മാർക്ക് ചെയ്യുന്നതിനാണ് കോൺസ്റ്റലേഷൻ എന്ന് പറയുന്നത്. So we will study about constellation diagrams of different modulation schemes. So this is the concept. Constellation എന്ന് പറഞ്ഞാൽ സിഗ്നൽ സ്പേസിൽ ഒരു സിഗ്നൽ എന്തായാലും ഒരു പോയിൻ്റ് ആണെന്ന് പറഞ്ഞു. സിഗ്നൽ സ്പേസിൽ ആ പോയിൻ്റ് എല്ലാം കൂടെ മാർക്ക് ചെയ്ത് വെക്കുന്നത് ആ റെപ്രസെൻറ്റേഷൻ n ഡയമെൻഷണൽ സ്പേസിൽ. നമുക്ക് 2D 3D ഒക്കെ വരയ്ക്കാൻ പറ്റുള്ളൂ. n ഡയമെൻഷൻ നമ്മൾ ഇമാജിൻ ചെയ്യുക. ഒരു n ട്യൂപ്പിളാണ്. ഒരു പോയിൻ്റ് എന്ന് പറഞ്ഞാൽ n ട്യൂപ്പിൾസ് ഉണ്ട്. ആ പോയിൻറ്റിൻ്റെ റെപ്രസെൻറ്റേഷൻ എല്ലാ ക്യാപിറ്റൽ എം സിഗ്നൽസിൻ്റെയും നമ്മൾ ഈ n ഡയമെൻഷൻ സ്പേസിൽ ഓരോ പോയിൻ്റായിട്ട് റെപ്രസെൻറ്റ് ചെയ്യുന്ന ആ ഡയഗ്രത്തിനാണ് കോൺസ്റ്റലേഷൻ ഡയഗ്രം എന്ന് പറയുന്നത്. So this Sm is called the signal space, the vector Sm is called signal space representation or constellation. Now we'll study some of the properties. You know that energy of the signal is integral minus infinity to infinity Sm of t the whole square dt modulus. Now this Sm is actually Smn phi 1 of t, Sm1 phi 1 of t plus Sm2 phi 2 of t plus etc. Smn phi n of t. All these phi m are orthogonal to each other, and also they have modulus 1. So if you are using that property, that is orthonormality, all the basis functions are having modulus 1 or energy 1 or norm 1, and also they are orthogonal to each other. If you are using that, you can find that this energy of the signal is equal to sigma n equal to 1 to capital Smn square, or it is the norm square of that vector. Okay, so the energy of the signal can be found out by squaring all the coefficients and adding it. It's a very important property and we will be using in the future lectures. ഒരു സിഗ്നലിൻ്റെ എനർജി കണ്ടുപിടിക്കാനായിട്ട് അതിൻ്റെ സിഗ്നൽ സ്പേസ് അല്ലെങ്കിൽ വെക്ടർ റെപ്രസെൻറ്റേഷൻ എടുക്കുക, അതിൻ്റെ എല്ലാം കൂടെ സ്ക്വയർ ചെയ്യുക, ആഡ് ചെയ്യുക. അല്ലാന്നുണ്ടെങ്കിൽ അതിൽ നിന്ന് ഒറിജിനിലേക്കുള്ള ദൂരം കണ്ടുപിടിക്കുക, അതിനെ സ്ക്വയർ ചെയ്യുക. സോ ദാറ്റ് ഈസ് ദ എനർജി ഓഫ് സിഗ്നൽ. Now any signal can be represented as a point on the signal space spanned by phi n of t, sigma n equal to n equal to 1 to n. ഈ phi n of t എന്ന് പറയുന്ന ബേസിസ് ഫംഗ്ഷൻ വെച്ചിട്ട് എസ് എം ഓഫ് ടിയിലെ ഏത് എം സിഗ്നൽ, ഈ എം സിഗ്നലിലെ ഏത് വേണോ phi n of t വെച്ച് റെപ്രസെൻറ്റ് ചെയ്യാൻ പറ്റും. എനർജി ഈസ് ദ സ്ക്വയർഡ് നോം. Now consider two signals sk of t and sl of t. Now you are trying to find the inner product of sk of t and sl of t. So sk of t you can substitute as sigma n equal to 1 to n skn phi n of t. sl of t you can substitute as sigma n equal to 1 sln phi n of t. So അതിൻ്റെ ഇന്നർ പ്രോഡക്റ്റ് കണ്ടുപിടിക്കാനായിട്ട് ഇൻ്റഗ്രൽ മൈനസ് ഇൻഫിനിറ്റി ടു ഇൻഫിനിറ്റി sk of t sl of t is actually sigma. You do some, or you substitute for sk of t and sl of t and do some small manipulations, then you will get it as sigma n equal to 1 to capital N skn sln, because phi n of t and phi k of t, they either become 0 or when they are multiplied, or when those two coefficients are equal, it is 1. When k and l are equal, it is 1. So you will get the inner product as sigma n equal to 1 to n skn into sln. So you can see that you are multiplying the coefficients and adding. രണ്ട് വെക്ടർ എടുത്തിട്ട് അതിൻ്റെ കോഎഫിഷ്യൻസ് തമ്മിൽ മൾട്ടിപ്ലൈ ചെയ്യുന്നു, അത് ആഡ് ചെയ്യുന്നു, പർട്ടിക്കുലർ കോഎഫിഷ്യൻസ് തമ്മിൽ മൾട്ടിപ്ലൈ ചെയ്യുന്നു. ദാറ്റ് ഈസ് ആക്ച്വലി ദ ഡോട്ട് പ്രോഡക്റ്റ്. So you can see that this is actually the dot product of the vectors sk and sl. So the most important thing is that the inner product of two signals is actually the dot product of the corresponding vectors in the signal space. So that is an important property. നമ്മളൊരു സിഗ്നലിൻ്റെ ഇന്നർ പ്രോഡക്റ്റ്, രണ്ട് സിഗ്നലിൻ്റെ ഇന്നർ പ്രോഡക്റ്റ് എടുക്കണമെങ്കിൽ ഈ സിഗ്നലിന് സിഗ്നൽ സ്പേസിലുള്ള അതിൻ്റെ വെക്ടർ റെപ്രസെൻറ്റേഷൻ കണ്ടുപിടിക്കുക, രണ്ട് സിഗ്നലിൻ്റെയും, അത് തമ്മിലൊരു ഡോട്ട് പ്രോഡക്റ്റ് എടുത്താൽ മതി. സിഗ്നലിൻ്റെ എനർജിയാണ് കണ്ടുപിടിക്കേണ്ടതെങ്കിൽ ആ സിഗ്നൽ സ്പേസിലുള്ള റെപ്രസെൻറ്റേഷൻ എടുക്കുക, അത് സ്ക്വയർ ചെയ്യുക, അതെല്ലാം കൂടെ ആഡ് ചെയ്യുക. ദാറ്റ് വിൽ ഗിവ് യു ദ എനർജി. നൗ വി നീഡ് ടു നോട്ട് ദാറ്റ് the Gram-Schmidt procedure may give different basis functions based on the order of choosing S1 to Sm. ഇപ്പോൾ നമ്മളിവിടെ S1 of t തുടങ്ങി S2 S3 S4 എന്ന ആ ഓർഡറിലാണ് പോയത്. നമുക്ക് അങ്ങനെ തന്നെ ചെയ്യണമെന്നില്ല, S2 തുടങ്ങാം, S3 തുടങ്ങാം. അപ്പോൾ എങ്ങനെ ഏതിൽ തുടങ്ങിയാൽ ഡിഫറെൻറ്റ് ആയിട്ടുള്ള ബേസിസ് ഫംഗ്ഷൻ കിട്ടും. ബട്ട് ദ ഇമ്പോർട്ടൻറ്റ് തിങ് ഈസ് ദ ഡയമെൻഷനാലിറ്റി റിമെയിൻസ് ദ സെയിം. ഇപ്പോൾ ഈ കേസിൽ 4 ക്യാപിറ്റൽ എം എന്ന് പറഞ്ഞാൽ 4ഉം ക്യാപിറ്റൽ എൻ എന്ന് പറഞ്ഞാൽ 3ഉം ആയിരുന്നു. അതൊരിക്കലും മാറില്ല. നമ്മൾ ഏത് ഓർഡർ ചൂസ് ചെയ്താലും ദ ഡയമെൻഷനാലിറ്റി റിമെയിൻസ് ദ സെയിം, ബട്ട് ദ Gram-Schmidt procedure may give different basis functions based on the order of choosing Si of t. ഓക്കെ, നമ്മൾ ഏത് ഓർഡറിലാണോ ചൂസ് ചെയ്യുന്നത് അതനുസരിച്ച് ബേസിസ് ഫങ്ഷൻസ് മാറാം, ബട്ട് ദ ഡയമെൻഷനാലിറ്റി റിമെയിൻസ് ദ സെയിം. ഓക്കെ, I'll stop here. We'll continue the next class.